All right, so now we'll go ahead and go through the slides. So just to simply square up the rest of the parts to understand Big O and go over the rules of how do we figure out what a random algorithm's Big O runtime is anyway, right? Because you're looking at something, you're going, oh my god, how am I going to figure all this Big O stuff out? It's actually ridiculously easy for most of the algorithms you encounter. And then you'll learn in algorithms, if you take 3223, you'll learn basically there's a master theorem for figuring out the runtime. All right, so Big O notation is actually fairly straightforward. Right, here's our search algorithm we went over ourselves, except they used an array, right? And what they do over here is that they're just using an integer and they're returning the index, right? And it's saying basically that if the target isn't present, this loop runs x.length number of times. If there's n items, this will run n times, so we check n things. So this is a O of n algorithm because the growth rate is O of n. Right. Note over here that actually that it brings up something interesting, that we have two growth rates, where basically that we're checking if they're different. Right. What this is checking is that, hey, are all the items in in Y, do they occur in X? So we're taking each item and we're checking if it's in Y. So this is actually X times Y. It's X dot length times Y dot length. Now we're not going to see too many examples of these in class, but the big O of this is N times M, where basically we're essentially, and here as opposed to O of N squared. And the reason being it's N times M is because we're assuming that X's size can be drastically different than Y's size. So, all right. This is the example of a quadratic algorithm called R-unique, where basically we're checking every pair against every other pair, right? This is similar to the one you had to write for homework, right? You're checking each pair. So for every item in the list, we check it against every other item in the list, and that's a quadratic growth rate, right? And again, the quadratic growth rate is going to look something, let's see, new canvas. Let's go ahead and create a new canvas. It's going to look something along the lines of this, right, where we have our time, t, and the number of items, n. It's going to look, a quadratic growth rate looks something like this, a quadratic algorithm, right, a bit of a parabola in there, right, or it might look like this, something a bit slower, right, or it might look like this, right, but they're all going to look like parabolas, essentially. Okay, so now how do we analyze this, right? The idea here is that you can think of this as the orders of it's a big O can be thought of an order of magnitude. It's kind of the order of magnitude for the worst case scenario is a lot of the times what we're looking at here. In fact, this is a total lie. And what I'm saying over here, there's actually, no, that's not a total lie. Big O really means worst case, but a lot of times you're gonna see big O used for average case, and that's a total lie. Big O, in fact, the mathematicians are really having a hard time with me right now because they'd probably hate the way I'm explaining this, but it's what I'm trying to do is give you an intuitive understanding before we go into the rigorous mathematical understanding of this. Okay, so here's your so basically there's two big things you just have to do in order to figure out what the big O runtime and algorithm is. The first trick is count the nested loops. A single loop, if it goes over the entire array, it's going to be an O of n algorithm. If you've got a pair of nested loops, right, like we did for over here, right, nested loop, each loop goes over the entire array, then it's going to be O of n squared. And we demonstrated even though that this one doesn't go quite over the entire array all the time, it goes over the entire array, then one less than that, then one less than that, then one less than that. That's still, we demonstrated that that's still O of n squared. So if you had three nested loops, one loop inside another loop, that's n to the cube. So, and these are again assuming the loop goes over the entire thing, the entire list or the entire algorithm. Okay. And this gets into log time, but I'm going to save that for recursion because it actually makes way more sense when we're dealing with recursion. Okay, so what's the runtime of this guy? Right, so this is let's take a look at this. This is a simple statement that gets executed n squared number of times over here, this part over here. So you've got n squared over here. Then you've got essentially 5 simple statements that get executed n number of times. And then we've got 25 statements over here. For a grand total, we can say that the time this algorithm, the number of steps this algorithm takes, Tn, is equal to n squared plus 5n plus 25. All right, and so here's the formal definition of Tn, of big O. We're saying that basically the time this algorithm is going to take is not going to be any worse than some function of n. And this is saying there exist two consonants n naught and c that are both greater than 0, and they're a function such that at some n greater than n naught, that constant times the function is equal to t of n. What this means, and it took me a while to understand this, is that basically that your function over here, there's going to be some function that we can get it under, essentially, that we can draw it and we can get it under, or we can add constants and we can just squeeze it under on the graph. Right? That essentially means that suppose this is our t of n over here, right? This is our t of n over here. That means in terms of big O notation, right? This is an O of n squared. Let's assume this is an O of n squared as opposed to some like O of n cubed or something. That means I can draw some other O of n squared algorithm. Right? I can draw this guy and say, hey, my guy is going to do no more worse than this O of n squared graph that I just drew. Or I can say, or if we zoom in here, let's see. I think I just have to, come on. Let's see. Yep. Or I can zoom in here and say, so the whole n naught thing means essentially that I can come in here and say, okay, so at some point, this other algorithm, right, I might be worse than this other algorithm. I may be better, but I'm never going to be worse than this other algorithm at this point, right, after some point. So the other way of explaining this that's not graphically is that once n gets sufficiently large, there's always going to be a constant basically that the t of n is going to be less than or equal to than this function, right? Once n gets sufficiently large, we're going to say it's going to be under some other n squared algorithm. It's going to never perform worse than that. It's essentially saying you're never going to be worse than this. Example, right? And so this brings us to our second rule for figuring out the runtime, right? We said that the Tn was n squared plus 5n plus 25. So the second rule to figuring out the order of magnitude for times is that we basically throw away, and I basically mentioned this before, I implied it heavily, we throw away anything that's not the largest exponent. So we don't say O of n squared plus 5n plus 25. We just say O of n squared. And this will make your first page of homework some of the easiest homework you've done in a long, long time. All right. So how do we show this? We show for n squared plus 5n, show that this is O of n squared. All we have to do is find an n naught and c such that basically that this is at some point it's greater than that. So we have to find the point where c of n squared is greater than n squared plus 5n plus 25. And all you have to do is just set them equal to each other, and you can work through it yourself because we're not going to do it in our class, but it's fairly straightforward. This is something you learn in math concepts. But the idea here is that they realize, oh, if we set n naught to this, we set n to n naught, so we set all these to n naught, divide over here by n naught, so this becomes 1, this becomes, you get n over n naught over n naught squared, or 5n naught over n naught squared. So those cancel each other. So you get some canceling, and you get 5 over n naught, and then plus 25 over n naught squared over here. So then we've got so that gives us an equation for our constant. And so we say if we set n naught to 5, right? Then then we get 3 for c. And so then if we draw that, we see basically at some point after 5, basically our function squeezes under, right? Our function squeezes under this performance. So the entire point of this is a roundabout way of saying what I was saying from the beginning. We can draw some other function of the same magnitude that our function will be able to squeeze under, and we can point to that function and say our function is never going to be worse, is not going to be worse than this once we get up to a big enough size. Right? Our function is never going to be worse than this other function that we just happened to draw. All right? So, essentially you've got t of n, which means the amount of items the amount of steps your item is going to take. And then you've got the order of magnitude, which is basically the upper limit of performance. Now, these are all the and again, so what we've learned, so that's a bunch of math. And I've been trying to keep this grounded in practical stuff as much as possible. We've got constant time, which is O of 1. We've got linear time, which is O of n, which means essentially a single for loop, basically doing something for every single item, doing a set amount of work for every item in a list. And quadratic, which means that we do for each of the n items in the list, we have to do n amount of work on it. Now there's these other ones we're going to learn, log of n, but we're going to learn that when we tackle recursion. And then after we learn recursion, when we get into sorting, we'll learn about n log n. Okay? Now, right now we're going to... So, actually, better split off this for a separate video.